Welcome to lecture 4, Incompressible fluid flow related to fluid drive. This is under module 2, Fundamentals of fluid flow and properties. Control volume method is applied in analysis of fluid power in general. This is because the movements of fluid particles in a space are not much of our interests, as in general fluid mechanics based on Newtonian theory. Rather, we are interested in the movement of volume of fluid through the conduit. Now, let us consider conservation of mass. The rate of mass flow into the control volume equals the rate of mass flow out plus the rate at which mass accumulates inside. Now, let us consider a control volume. Fluid is flowing inside this volume, and then we consider a velocity in normal direction at a point on the volume which is V n, and obviously which is having a straight component V. Now, mathematically we can write rho V n d A s is equal to minus d m C V by d t is equal to minus d by d t integration of rho d v. Now, in this case A s is the normal surface area, rho is the density which we have already discussed, V n is the normal velocity, and this normal velocity, it is importantly is positive when directed outwards. That means, the direction shown is positive. That must be equal to time rate of change of accumulated mass in control volume. M C V is the accumulated mass. Now, this means that the minus sign is given here. The reason is that if the mass is accumulated inside, then V n will be in the opposite directions. If it is going out, then it will be minus. That must be equal to the elemental mass of control volume. We should consider the rate of change of elementary mass of control volume. Now, application of this conservation of mass or momentum theory is that, let us consider a simple conduit, a vessels with a conduit. Now, flow in to this control volume through the left side, where the area is A 1, V 1 is the velocity, and the area, surface area of this vessel is A t, and height of a datum line is L, where the area is A2 and velocity is V2. This means that along this line, when the flow is going in, velocity is V1, flow is going out, velocity is V2. Area of this outlet is A2, area of this inlet is A1, and AT is the surface area of this vessel, and L is the height from this datum line. Now, for steady state condition, we can write rho V1 A1 is equal to rho V2 A2. What does it mean, the steady state conditions? That there will be no change in this volume, where L is not varying. Now, for unsteady flow into tank, that is this vessel, L will vary and the expression becomes rho V1 A1 minus rho V2 A2 is equal to rho A2 dL by dt. This means dL by dt will be positive if this height is increasing, and this is automatically it will be negative if L is decreasing. Now, conservation of momentum. The rate of change of momentum of the system in any direction is expressed as the sum of the rate of change of momentum of the material inside the control volume, which we have considered as a V A, small V A, in the same direction, and net rate of outflow of momentum through the control surface in the same direction. It is expressed as f x is equal to d by dt integration of rho v x dVA over the volume V A, the control volume V A. This V x is the velocity in x directions, plus rho integration of rho V x V n and d A s. It will be in the y directions. As you look into these equations, only we will considering here the expression is same, velocity in y direction, and here also we consider the velocity in y directions. Similarly, in z directions we consider velocity z here and also here. For steady flow, first term of right hand side is 0. If it is a steady flow, then there will be no change in this, whereas there may change in this surface area, and accordingly these equations will be reduced. Now, steady flow example. Let us consider another tank. It is a closed, it is having a inlet and a outlet. Now, let us consider at the inlet area is A1, oil is having density rho 1 and velocity V1. At outlet it is rho 2, velocity V2 and area is A2. Now, rho 1 and rho 2 may be equal for incompressible fluid if there is no change in temperature. Now, for this type of flow you will find that if we do not apply a load, this will move, because this velocity obviously will be higher than this and a force will be generated here. Now, to balance this for equilibrium we apply a load F x, and therefore, the relation we can write inflow of x momentum is equal to V 1 rho 1 A 1 V 1, that is equal to rho 1 A 1 V 1 square. Is it clear? This is the volume flow rate and with the velocity. So, we get this is the x momentum. Similarly, outflow we get it rho 2 A 2 V 2 square. Now, equating we get the external force F x is equal to rho 2 A 2 V 2 square minus rho 1 A 1 V 1 square. This means that we have to apply this force for the equilibrium of this body. Let pressure condition be P 1 is equal to P 2. This means that here pressure and here pressure will be same. Then from continuity consideration, incompressible flow rho 1 A 1 V 2 is equal to rho 2 A 2 V 2, and therefore, F x will be rho 1 A 1 V 1 V 2 minus V 1. I think I have made a mistake, it is not pressure conditions. The pressure conditions remain same, for which rho 1 and rho 2 remain same. Here I would like to mention the pressure remains same as well as temperature also remains same. So, that we get rho 1 is equal to rho 2. Now, unsteady flow example. How the pressure difference P 1 minus P 2 is related to rate of change of flow rate of a frictionless incompressible fluid in a uniform tube of length L. We have considered a tube, circular tube, and we have taken a segment of length L. This is of uniform cross sectional area A, and the tube is also rigid. Now, flow in is Q 1 and flow out is Q 2, and we also for generality we consider that density here was rho 1 and density this side is rho 2, pressure is here P 1 and P 2. We consider that pressure is changing. Maintaining continuity, we can write rho Q 1 is equal to rho Q 2. Again in this case we have considered rho 1 is equal to rho 2, that means density is not changing. In most of the fluid power analysis, for small conduit, if length is not very large and if there is not too much change in pressure and the temperature, then we may consider rho 1 is equal to rho 2. This simplicity is required to avoid the complication in the calculations, and in most of the cases the error will be negligibly small. Therefore, we can write Q 1 minus Q 2 is equal to 0. This is for incompressible fluid. Now, the momentum equation gives P1A minus P2A is equal to rho q v minus rho q v minus d by dt rho A L v. A into L is the volume, v is the velocity and rho is the density, that is the mass. So, rate of change of mass minus the mass in. Now, this gives clearly P 1 minus P 2 into A, that is the force, is equal to rho A L d by dt q by A. If you equate this, we will arrive here, and this gives clearly rho L dq by dt as A is constant. This A will cancel out. This means that the force, net force available due to this flow is mass density into length into time rate of change of flow. This q is flow rate. So, this is time rate of change of flow rate. So, final equations is coming P 1 minus P 2 rho L A dq by dt. Conservation of angular momentum. In a steady flow centrifugal pump, let V T 1 is the tangential velocity at radius r 1 at entry. If you think of the centrifugal pump, then you will find that entry at the towards the center and outlet is towards the outer periphery. Now, in fact, it works on hydrokinetic energy. In that case, when the impeller inside is rotating with the volume of fluid, initially there is air, then this fluid mass gets momentum and it is discharged outside. In turns, it creates a suction pressure at the inlet. Anyway, after let us consider it is pumping an incompressible fluid. In that case, let V T 1 is the tangential velocity at radius r at entry. This means that if I consider a circle at the entry, then tangential velocity of the mass of the fluid, again let us consider a control volume. Now, same thing when it is being discharged, the tangential velocity is V T 2 at radius r 2. Then we can write the ideal input torque is equal to T is equal to R 2 V T 2 minus R 1 V T 1 into rho, again density, into the flow rate. Now, let us consider one dimensional frictionless and incompressible streamline flow with area change. Now, in this case again we have considered a conduit which is having inlet area is A 1, outlet area is A 2. In this closed vessel or closed tank, let us consider at the inlet the U1 is the intrinsic internal energy per unit mass of fluid. Now, this is a little difficult to have the concept, because inside the fluid the internal intrinsic internal energy may change while it is flowing from one side to the other due to addition of some external energy or going out the energy from the inside of the conduit or the control volume. Now, this one again having a density rho 1, velocity v 1, pressure p 1, z 1 is the height of this fluid from a datum line, and w is the weight flow rate of fluid. Okay. In outlet side also we consider u 2, rho 2, v 2, a 2, p 2, z 2 and w. Clearly, this in this case what we have considered in this system, that z 1 is equal to z 2, because this is a horizontally placed, we have neglect that part, and rho 1 is also is equal to rho 2, because there is the change in pressure not changing the density, or whatever change is there, that is negligibly small. And also u 1 and u 2, that means there is no change in intrinsic internal energy. Now, then simply we can develop these equations, and we can neglect also z 1 and z 2 as they are equal of these equations. Now, these equations is very well known equations, Bernoulli's equations, and with this equation we will see next that if we now add some energy, then what will be the changes in these equations. Now, here as I have told, this is a frictionless, that means there is no friction between the fluid and the conduit. We have neglected that part, that is there, always there in a conduit, there will be friction, but we have neglected that one. And again this is we are what we are developing this equation, that is for the incompressible streamline flow, no turbulent flow also, then equation will be different. Only thing, there will be change in area. Now, what we have done, we have added some external work. So, that is symbolized by this. Say let us consider that we are a fan or impeller is being driven, and it is a energy being added there. Okay. Now, also we are adding some heat, and there is also this is the heat flow inside. Now, why we are considering such things? The in fluid power usually this external work will be there on the fluid, and this heat is automatically generated due to the temperature rise, due to the change in pressure, due to the change in internal energy, that we can consider in this form. As well, in some cases heat also added from the outside. So, what will be the equation? Now, we introduce the energy equation and using the control volume concept. Then what we find that the same equation which we have considered earlier, we consider this u 1 and u 2, we consider that there will be change in this intrinsic energy. As we are working on that, we are also adding the heat, and we have also kept in this height term here, and then the energy added is written in this form. this is the work added to this minus dQH by dt divided by W by G. Now, Ws is the shaft or shear work done and QH the heat flow to control volume. Here the question is that if we why it is negative, the heat flow in actually reduces this energy. Now, if we do not add any external work to the system, then dx by dt is equal to 0. Therefore, the total equation will be reduced in this form. Obviously, we have considered Z 1 is equal to Z 2. And we can write dQH by dt is equal to W by G U 2 minus U 1 is equal to W by G CH T 2 minus T 1, whereas CH is the specific heat, T 1 is equal to temperature before heating and T 2 is equal to temperature after heating. Now, we consider frictionless flow through nozzles and orifices. Now, here we have considered again a vessels or large reservoir, and where we are having a small hole which is an orifice. Now, this is known theory to you. You will find that oil will flow out and you will find that the stream will have a little less area than the orifice area at a certain distance, and then again this area will increase. Now, the minimum area, as you know, it is called vena contracta. Now, for this one we can write the equation in this form. Here the velocity at the entry we may consider 0. We are considering this area a little away in the left side from the orifice, and then we are considering the velocity V 2 at the vena contracta. Then this equation can be written in this form. That means, velocity here we can write 2 by rho P 1 minus P 2. Therefore, the mass flow rate can be written in the form of rho into Q is equal to rho A 2 into V 2, because A 2 is the area here, is equal to rho A 2 square root of 2 by rho P 1 minus P 2. Now, the A 2 is the area at the vena contracta, which is not known. It is neither we can measure the area there. Now, to take care of that, what we do, that rho q into C d into A 0 square root of twice rho P 1 minus P 2, where C d is the coefficient of discharge and A 0 is the area of the orifice. Now, again you know that coefficient of discharge is equal to the area contraction coefficient and another coefficient of velocity. So, combining this CD we use for fluid flow. Now, in case of fluid power with incompressible flow for a suitable orifice, normally this CD value remain more or less constant. Of course, that depends on the orifice area. In most of the calculation in fluid power, particularly in oil hydraulics, this CD value may be taken as 0.62. Later, when we will come to valve flow, I will show you that how CD can be taken more or less constant for fluid power analysis. Also, a care is taken to make the orifice. There are various type of orifice in fluid power components, starting from a circular hole to the variable area, but the care is taken so that CD more or less remain constant. The final equation here, the 2.4.24 is Q is equal to CD A 0 square root of 2 by rho P 1 minus P 2. This we should remember, because very often we need to use this equation. Other equations which I have shown, normally when we analyze the inside flow in a valve, then it will be required, but normal cases this equation will be more useful. Now, viscous flow through the capillary passage. Now, here one important factor we consider, which is Reynolds number. Reynolds, as you know, is a scientist. He developed these equations where R is equal to U d by rho. Now, this is kinematic viscosity. Already we know that this is dynamic viscosity by density. Here of course, we have used in other form, normally we use rho. Now, U is equal to the velocity of fluid in conduit. Now, normally this Reynolds number becomes very high, where d we consider d is equal to hydraulic diameter, that is equal to 4 into flow section area. Whatever may be the area, we consider 4 into flow section area divided by flow section perimeter. Let us consider it is a circular one. Then what we will do, 4 into pi r square divided by 2 pi r, 4 into pi r square divided by 2 pi r. So, this becomes 2 pi r, that is equal to pi d. So, this is hydraulic diameter. Now, in case of fluid power, we consider a reduced Reynolds number, which is expressed as R star is equal to U L by sorry, this is not rho, nu into H by L whole square. Normally, you will find this is much less than 1, and where the L is the length of capillary passage and H is equal to height of the gap or capillary passage. This is for an example. Even in a pipe, we can consider L is the length and H simply the inside diameter of the conduit, but this is more useful where the flow between two parallel plates or some capillary passage. Now, with this I finish this lecture, and this note is prepared based on these two books, The Control of Fluid Power by Martin and McCloy, and Blackburn, Rethoff and Shearer by Fluid Power Control. Also I have followed the another book, Hydraulic Control System, which is by Merritt, but most of the equations that I have followed from these two books. Thank you.